Assalamu alaikum students, welcome to my channel Physics with Hasnain. We have learned that thermodynamic state of a simple system can be described by its internal energy. However, internal energy is not the only useful way to describe a system. Thermodynamics introduces three additional state functions known as thermodynamic potentials. Think of these as different lenses for viewing the same physical system. These are enthalpy, Helmholtz Free Energy and Gibbs Free Energy, represented by H, F and G respectively. Here are their definitions. Enthalpy is defined as H is equal to U plus PV. Helmholtz free energy is defined as F is equal to U minus Ts, and Gibbs free energy is defined as G is equal to U plus PV minus Ts. At first, these definitions may appear artificial. Why would anyone add or subtract terms like pressure times volume and temperature times entropy? The answer lies in their natural variables. Each potential is naturally a function of a specific set of variables. Internal energy is naturally a function of entropy and volume. Enthalpy is naturally a function of entropy and pressure, whereas Helmholtz free energy is naturally a function of temperature and volume. And Gibbs free energy is naturally a function of temperature and pressure. But why do we need so many different functions? The answer lies in the variables that are easiest to control in an experiment. The natural variables for internal energy are entropy and volume, while we can control volume easily by using a piston. Entropy is extremely difficult to measure or control directly in a lab. Therefore, using internal energy as a function of entropy and volume for everyday calculation is very inconvenient. Thermodynamic potentials are constructed mathematically to replace entropy with temperature, which is easiest to control. Let's look at specific examples. Imagine a chemical reaction happening in a beaker open to the atmosphere. The pressure is constant. If the reaction releases heat, the volume must change, meaning the system does work on the surrounding. If we had only used internal energy, calculating the total heat released would be tricky because we would have to account for the expansion work. Enthalpy solves this. At constant pressure, the change in enthalpy equals the heat absorbed or released by the reaction. Chemists love enthalpy because they can measure it directly without a coffee cup calorimeter, without worrying about volume changes. Next, why we need Helmholtz free energy. Consider a battery operating in a room kept at a constant temperature, an isothermal process. Some of the internal energy of the battery is used to do work, but some is unavoidable lost as waste heat to the environment due to entropy. Helmholtz free energy solves this. The decrease in Helmholtz free energy tells us the maximum amount of work we can get from a system at constant temperature. Engineers use this to calculate the theoretical limit of engines and batteries. Next, what is the importance of Gibbs free energy? Most chemical reactions in a lab happen in a flask open to the air. This means both temperature and pressure are constant. Does a reaction happen spontaneously? Gibbs free energy solves this. The change in Gibbs free energy tells us whether a reaction is spontaneous at constant temperature and pressure. If the change in Gibbs free energy is less than zero, the reaction happens spontaneously. If the change in Gibbs free energy is greater than zero, the reaction will not happen. This is arguably the most important equation in chemistry. Thus, thermodynamic potentials do not introduce new physics. They simply provide different mathematical descriptions of the same system, each tailored to a particular set of experimental conditions.